Dear students, in the today's lecture, we are going to discuss forced oscillations. What are forced oscillations? When you are applying a periodic force on your body, then the body vibrates with the frequency of applied periodic force. Those vibrations are known as forced vibrations. If you are applying periodic force, for example, F sin theta, why we are expressing the periodic force as a F sin pt? If you are taking a force which is not varying with the time, then we can express it as a F. If it is varying with the time, then we have to write it as a function of time. If it is varying periodically, then we can write that force as F sin Pt or F cos Pt. What is this P? Frequency of the applied periodic force. For example, we are applying a periodic force of F sin Pt, then the body vibrates with frequency of P. What is this P? Frequency of applied periodic force. Now we are analyzing this forced vibration concept by using simulations provided by Professor Surendranath sir. We are very much thankful to him. So now I will show the animations provided by Professor Surendranath sir. See here, this one represents the system parameters. That means this spring loaded with mass, its natural frequency is 5 Hz and amplitude is 50 Hz. And this one gives the what is the periodic force you are applying. The frequency 0 means it is just force not varying with time. If you are giving some frequency value, then it provides the frequency of the periodic force. And this one is the damping factor. So in case of forced vibrations, there are three forces are acting here. One is a restoring force that is always associated with the system. And second one is a resistive force that is due to friction between the oscillating body and surrounding media that provides the damping effect. So that is we can give it as a form of damping quotient in this concept here. And third one is a periodic force. So that's the what is the force we are applying. For example, I have taken the system with 40 units amplitude and frequencies 4 Hz here. Now I'm applying a periodic force. The periodic force amplitude, for example, it is 40 units only, and frequency is for suppose 1 Hz, 2 Hz. So now another factor we are having is damping effect. We will consider the damping coefficient equal to 0.0 in this case, 0.2 in this case, and frequency have applied is 2H. Then the system oscillates with the frequency of applied periodic force. The system oscillates with the frequency of applied periodic force. That means the system oscillates with the frequency of 2H here. So now I will show here. In this case, the red color represents the damping effect, green color represents the periodic force, that blue color is the actual oscillation of the system here. Okay, so now you see here, it's after some time, the system will come to stable. Now the system oscillates with the frequency of 2 Hz here, that blue color here. But suppose here we are applying the frequency is 4 Hz only. Now I will increase the frequency to 4 Hz only. Then if you see here, the amplitude increases here. Earlier amplitude is not this much. In this case, if you observe here, the periodic force that is green color and damping effect, the red color, both are equal and opposite, they cancelled out. That's why the maximum frequency. Now it comes to stable position. It oscillates with the maximum amplitude. See here. The frequency is 4H, but amplitude is high in this case. Why the amplitude is high in this case? Why the amplitude is high in this case is if the natural frequency of the system and frequency of the applied periodic force both are equal, then the system is in resonance. And the system in resonance, it oscillates with the maximum amplitude here. In this resonance case, if you observe here, that means the applied periodic force frequency is P. The natural frequency of the oscillator is omega. If P equal to omega, then what is the situation if you observe here? The starting position, if you observe here, I will show the starting position here. See here. The both are here, it start from here and this one start from here. There is a phase difference occurs starting position. So those phase difference also we are going to analyze in this concept. So at that time I may not show this figure. That's why I'm showing this figure now only. So that can be analyzed during the discussion of this concept here. So now in case of force oscillations, there are three forces are acting. One is a restoring force, that is minus kx, and resistive force, that is directly proportional to the velocity and opposite in direction. The proportional replaces by constant gamma known as a damping coefficient. And third force here we are sorry, the third force acting in the system is the applied periodic force, that have written it as a F sin Pt. This F gives the amplitude of that force, and P is the frequency of the applied periodic force. Okay, and this is the F is the amplitude and P is the frequency of the applied periodic force. Here we have taken this one plus because it is supporting the oscillations, and these two are opposing here. That's why the total force acting is how much now? Minus kx minus gamma into dx by dt plus f sin beta. Sorry, f sin pt. That is the total force. So the total force acting. So the total force acting here is minus kx minus gamma into dx by dt plus f sin pt. But according to Newton's second law, F equal to ma, a is the acceleration, that can be written as d square x by dt square. Therefore, resultant force F equal to ma, that equal to m into d square x by dt square. Now we can equate these two. So m into d square x by dt square equal to minus kx minus gamma into dx by dt plus f sin pt. So we can take all the negative terms to left hand side and divide with m. Now see here, m into d square by dt square equal to minus kx minus gamma into dx by dt plus f sin pt. The positive term you can leave it right side, and negative terms you take it left hand side. Then m into d square by dt square plus gamma into dx by dt plus kx equal to f sin pt. Now we divide throughout with m. Then m will be cancelled here. Here we will get gamma by m. Here you will get k by m. Here you will get f by m. So d square by dt square plus gamma by m dx by dt plus k by m into x equal to f by m into sin pt. Now we can replace this gamma by m with 2b, that we have already done in the previous discussion of damped oscillations. And k by m, you know, that is always equal to omega square. Omega is the natural frequency. So now the final equation becomes d square x by dt square plus 2b into dx by dt plus omega square x equal to f by m into sin pt. Now we are going to solve this equation of motion of force oscillations. So the solution can be written as x equal to a sin pt minus pi here. So we can write the solution like this. How we can write the solution like this, sir? Because we know the resultant force oscillations are also having the same frequency of applied periodic force. So the frequency is a P here. That's why here also P. And amplitude we don't know, that value you have to find out. So we can write that amplitude as a K. And I already shown there is some phase difference between these force oscillations and applied periodic force. That's why we are introducing a phase term here, pi. Okay, that may be plus pi or minus pi. We can analyze with not an issue at all. That depends on the situation. So the solution can be written as x equal to a sin pt minus phi So now we have to find out the value of A and value of phi. Then we'll get the complete solution of equation motion of a force oscillation. So for that, we have to substitute this x value here. So that means we have to find out d square x by dt square. You have to find out dx by dt and x value this much. You substitute here. So now I am finding those values and substituting here. You see here. So this is the value of x and this is the value of dx by dt, sine derivative cos, and again differentiate once again, then d square by dt square. Here you know cos derivative minus sine. Now we are substituting these values in the above equation there. Then what is the equation? This is the equation. Now we are replacing d square x by dt square with this value here, and dx by dt with this value here, and x with this value here. If you substitute there, then this is the equation. Now here also sine pt minus pi is there. Here also sine pt minus pi is there. Now we can take that sine term common here, and this is the cos term is separate. And at the same time, we are doing a simple manipulation here. We are subtracting a pi here and adding pi. If you are subtracting pi and adding pi, there is no change in the system. That's not a problem. That's why we can do like this. So now I have taken this right hand side, subtracting pi and adding pi. Okay, so now this can be considered as this is A and this is B. So sine of A plus B. Sine of A plus B, we can write it as sine A cos B plus cos A sine B. We can apply that formula and we can manipulate here. So now in this term we have taken sine pt minus pi is common here. Then here we are having minus p square A, and here we are having omega square A. We can take A also common here. So later we can do that one. And here cos pt minus pi and sine. So now right hand side sine of A plus B is there. We can apply that formula. Sine of A plus B equal to sine A cos B plus cos A sine B. See here. So now left hand is the term here, right hand side sine of pt minus A, that I can write it as a sine A cos B cos A sine. So sine A cos B plus cos A sine. And left hand side as it is here. Now we can equate the coefficients of sine pt minus pi and cos pt minus pi on both the sides. So now these two equations are equal means the coefficients of sine pt minus pi and cos pt minus pi are equal. So now the quotient of sine pt minus pi here is minus p square a plus omega square a. Here that is f by m into cos pi. So the left hand side sine pt minus pi coefficient minus p square a plus omega square a. Right hand side sine pt minus pi coefficient f by m cos pi. So equate. So minus p square a plus omega square a, in both the terms have taken a common, and this becomes omega square means p square. So a into omega square means p square equal to f by m cos pi. In the second term, the cos pt minus pi coefficient 2bp a, and right hand side cos pt minus pi coefficient f by m sin pi. So 2bpa equal to f by m sin pi. So in order to find out the value of a here, because there are two constants are there, one is a and pi. Now we are having two equations in a and pi. So now we have to find out a and pi values. So to find the value of a, we have to eliminate pi. To find the value of pi, we have to eliminate a. So now we are going to find the value of a. So to find the value of a, we have to eliminate pi. For that, what we are doing is we will square these two equations. If you square these two equations, here we are getting f square by m square cos square pi. Here f square by m square sin square pi. If you add both, sin square pi plus cos square pi becomes 1. Then right hand side the pi term will be eliminated. Then left hand side we are having a square omega square minus p square whole square plus 4b square p square a square is the left hand side. So in this way we can eliminate the pi term, then we will get the value of a. So now left hand side we squared this one, a square into omega square p square whole square plus 4b square p square a square. So in the both the term a square is common. I have taken a square common. Then here omega square p square whole square plus 4b square p square equal to f square m by m square cos square pi plus f square by m square sin square pi. So f square by m square if we take common, so then sin square pi plus cos square pi equal to 1. Now I have taken this term to right hand side. Then you can find the value of a. So a equal to square root of this value. So f square by m square square root f by m and the square root will come here. This is the expression for value of a. To find the value of pi, now I will divide the second term with the first term here. Then f by m will cancel. Sin pi by cos pi, tan pi. Tan pi equal to 2 bpa by a into omega square is minus p square. So then a will be cancelled. Then tan pi equal to 2bp by omega square minus p square. That we will discuss. So this is the one term. This is another term. Now I am dividing these two terms. This one by this one. Then f by m will cancel. Sin pi by cos pi equal to tan pi. Here this is 2bp into a by a into omega means p square. So a will cancel. Then this is the pi. So from this pi equal to this value. So in this way we got the value of a and pi. If you substitute this a and pi values in the actual solution, what have given? X equal to a sine pt minus pi. And that if you put the value of pi and a, you can get the actual solution. So this is the actual solution. So in place of a, we put this one. Here in place of pi, we'll put this. Now we will discuss the different cases here. If the case 1, p much less than omega. What is the meaning of p much less than omega? The frequency of the applied periodic force is very much less than the amplitude, frequency of the natural frequency of the system. If the frequency of the applied periodic force is very much less than the natural frequency of the system, then what will happen? There is no phase difference between the periodic force and the oscillating system. So both are in the same phase in that case. So in this case, what happened here? P is much less than omega. So P value is very less. So P square can be neglected when compared with the omega square. Then if you neglect P square and P square here, then what you will get here? Omega square whole square square root. So square root to square will cancel. Remaining terms are already neglected. Then that becomes f by m omega square is the value. And another case we are going to discuss is P equal to omega. What is the P equal to omega? I already told. When the natural frequency of the system and frequency of the applied periodic force both are equal, then the system oscillates with maximum amplitude. That situation is called resonance. This is the resonance condition that we will discuss later here. Okay. In this case, what happened here? P equal to omega substitute here, and this term will be this term becomes a 0 because P equal to omega means omega square equal to P square. So this term becomes a 0, then remaining term here. But in this case, what will happen? There is a phase difference of pi by 2 between these two. There is a phase difference of pi by 2 between the force oscillation and the applied periodic. And if P is much less than omega, so if P much less than omega case if we consider, but the situation will possible only when the damping effect is almost negligible. Otherwise, we never expect the P much less than, P much greater than omega. That means natural frequency system is very, very low. then we are applying very high frequency periodic force. The oscillations set in the system only when the damping effect is almost negligible. So in that case, what will happen here? So this is the situation here. In this case is significant only when the damping force are small. That is B is very, very small. In that case only this is possible. Otherwise, the system not sustain any oscillations here. But in this case, both are out of phase here. There is a phase difference of pi between the applied periodic force and forced oscillations. So these are the three different cases in case of forced oscillations. Now we are going to discuss the situation of resonance. What is a resonance? I already explained. If the natural frequency of the system and frequency of the applied periodic force are equal, then the system oscillates with maximum amplitude. This situation is called resonance. That resonance condition we are going to prove now. But important point here we have to remember here is the resonance occurs only when the damping effect is less. If damping effect is very high, at that time the resonance will not occur. That condition also we have to remember. That's why I will show these two conditions now for getting of a resonance. So in the resonance, the amplitude should be high. So now take the system here, the resonance, and this is the amplitude we already discussed. So in the resonance condition, amplitude should be high. When the amplitude should be high here, if the denominator is low. If denominator is low, then what will happen? A becomes high. That means amplitude is high. Amplitude high means the situation is resonance. So that's why we are going to prove the conditions of one is P equal to omega. P equal to omega means the frequency of the periodic force and natural frequency system. Another one is B is small. So these two conditions are just already announced here that we are going to discuss here. When any function is having a minimum at any position, at that situation, the first derivative should be 0. So at maxima and minima of any function, the first derivative should be 0. So now the function is the denominator. So at resonance, we are getting maximum amplitude. That means denominator should be low. That means at resonance, the denominator should be low. That means d by d omega of this value should be low. So now we are d by dp of this denominator value we are calculating, that should be 0. That means denominator is low means the first derivative of that function should be 0. So now d by dp of, because it is varying with p, because natural frequency system will not change, we are changing only applied periodic force frequency, that is P. So we have to differentiate that with respect to P, then that should be equal to 0. Then if you differentiate, we got this is the condition here after differentiation. After simplifying, this is the situation here. Now the product of two terms here. So 4P equal to 0 or the second term should be 0. So first term 4 not equal to 0, we know. If P equal to 0, that means frequency of the applied periodic force is 0. Then there is no periodic force at all. So definitely P not equal to 0. Then what will be 0? The second term. That means this term should be 0. If this term should be 0, you simplify here. This one equal to 0. Then from this you simplify, you are getting this. So in this case, this B should be low. Then if B should below only, then definitely b square value becomes very, very small. If b is small, then b square becomes very, very small. If b square is very, very small, we can neglect this term. Then p square equal to omega square, then p equal to omega. This is equation. So these are the two conditions we can explain by using this condition. At this case, how we can write a maximum value? So in a maximum is one is omega equal to p. So this term is 0. Then in this case, the value remains is 4b square p square square root, then 4 root 2 bp. So that's why f by m 2bp. And we know 2b equal to gamma by m. So if you put 2b equal to gamma by m here, m will cancel, f by gamma p. So that equal to f by gamma into omega. So the amplitude in case of resonance is inversely proportional to this damping coefficient. Damping coefficient is high, amplitude will be low. Yeah, damping coefficient is 0, amplitude becomes a maximum. So this case here, see here. So there are no damping. So there are no damping means the amplitude is infinite. That means undefined. So damping is low is like this. So with increase of damping, see here, the amplitude of the resonance condition is so at omega equal p square equal to 0 means omega equal to p, the resonance occurs. So this is the situation of resonance that can be analyzed by using this concept here. So now we are going to discuss one more important concept related to this resonance, that is sharpness of resonance. What is the meaning of sharpness of resonance here? First, if you see here, if this is the amplitude, this is the variation here, and if with the variation of frequency at the maximum point, the small variation will not affect much amplitude variation here. For suppose here, the amplitude is like this. Amplitude variation is like this here. In this case, what happened here? The small variation in the frequency, there is a large fall of amplitude here. And in this case, in the small variation of frequency at resonance condition, the fall in the amplitude is less. If the fall in the amplitude is high, then we can say sharpness is high. If the fall in the amplitude is low, then sharpness is low. So the sharpness is high or low, that depends on the variation of amplitude with the variation of frequency at about resonance situation or resonance conditions here. So that is the sharpness of resonance. So sharpness of resonance can be measured as change in amplitude by change in frequency. How we can measure the sharpness of the resonance? Change in amplitude by change in frequency. So here the situation here, resonance here, the then amplitude A equal to for a particular frequency other than resonant frequency. This is the amplitude here. Okay, because omega almost nearly equal to p square. That's why so omega is almost near, because we are considering the situation at resonance situation. So at resonance frequency, omega is almost equal to p here. So that's why here at exact resonance condition, A maximum omega equal to p. Now I am taking a frequency very nearer to the maximum condition. That means omega minus p value is very, very less. Then when compared with the omega square, p square value is very, very less. So we can neglect that value now, and we consider this term becomes almost 0. So if you consider this term equal to 0, then what remains here? 4b square minus p square. So that is the amplitude for a particular frequency nearer to the omega. Okay. So at omega, what is the frequency? What is the amplitude? This much. At omega equal to p, the amplitude is this much. Now we are finding the amplitude at a frequency very nearer to the omega, but not equal to omega, and very near to omega. That's why we have cancelled this term here. Omega square and p square value is very, very less. That's why square can be neglected here. So at that frequency p, f equal to gamma. So now how we can measure the sharpness of the resonance? Change in amplitude by change in frequency. So what is the amplitude at resonance? F equal to gamma omega. What is the amplitude very near to this resonance condition? f by gamma p. So what is the change in amplitude? This one minus this one. That means f by gamma omega minus f by gamma p. So if you take f by gamma common, 1 by omega means 1 by p. Then that value we can simplify, it will comes like this. Now, what is the frequency at resonance omega? What is the frequency nearer to that one? We named it as a p. So what is the change in frequency? P minus omega. So now the change in frequency is p minus omega. Now, sharpness of the resonance is change in amplitude by change in frequency. So the change in amplitude is this much and change in frequency this much. So if you divide these two, then p minus omega and this p minus omega cancel here. Then what is the sharpness resonance? F by gamma omega p. So sharpness of resonance also depends on damping coefficient. Damping coefficient is high, then sharpness is low. Damping coefficient is low, then sharpness is high. So here, if you already discussed in the this one, in this concept, if you observe here, in this case here, see, damping is high, then sharpness is low. Here damping is low, the sharpness is high. So in this way, the important concept related to resonance can be analyzed. Thank you for listening. Today we are going to stop this concept here. In the next class, we are going to discuss about shock waves.